Okay, today I want to talk a little bit about electroplating because how cool is it to plate metal out of either a liquid or a solution that looks like it doesn't have metal in it? I just think that that's so amazingly cool. So I want to talk a little bit about molten salts and electroplating and kind of look at another redox type application, kind of in the electrochemistry sort of realm. So molten salts are just any ionic compounds that are in their liquid form. Now, this is a very rare thing to think about a salt or an ionic compound being in its liquid form. We usually think about salts as being solids or being in solution, so they are mixed with water, so we think of them in the aqueous form. But to think of a liquid salt, that takes some pretty high temperatures. And when a salt, an ionic compound, is in its liquid form, unlike in its solid form, it actually will conduct electricity. So if I have sodium chloride here, which this is a really nice drawing of sodium chloride, as you can see, when it's in its solid form, then it has this nice, crystal structure. It has this orderly repeating array of unit cells of all of my different ions that are stacked together in kind of this best fit model where they're maximizing and minimizing repulsions and charges, and there's all that kind of going on. So we have this in the solid format. Now, when I increase the temperature, and we're talking to like the order of around 801 degrees Celsius, so high temperatures, then the ions are going to start to melt, right? So a solid goes to the liquid form, so the ions start to separate out a little bit more. We're increasing the space between them. That's what happens when we get to a liquid, is we have more free flowing of the particles moving around. The particles in this case are charged particles. So when I have the liquid form of sodium chloride, what I really have in solution is kind of this, I'm going from the liquid to the ions that are liquid in the liquid form, which is just a little bit wacky. Weird to think about. So now we have these ions in solution, and now this whole, or not in solution, sorry, in their liquid form. So they've undergone a phase change, and we have this liquid mass of sodium and chloride ions. Now, if I was to perform electrolysis here, electrolysis is when you run an electric current through something. So if I put in some electrodes, let's make this my negative, my anode, and this my positive, my cathode. Then at those electrodes, if we're running some electric current through this, then we're going to start to do some redox chemistry, because I have sodium ions that are in solution. Those sodium ions are going to accept an electron, the electrons that are moving around because of this electric current, and then they're going to give me sodium, like the metal. So you're going to plate out sodium metal, which is kind of wacky. So is this going to happen at the anode or the cathode? Remember that your anode is the negatively charged one, the cathode is the positively charged one. Well, this is going to happen where reduction occurs. So this is going to happen at the cathode, because reduction is gaining electrons. And at the same time, my chlorine, so if I have two of my chloride ions, then it's going to be losing, right? We're in the ionic form, we're in the anionic form here. We're forming chlorine gas. That's why we have two, so we're balancing this thing out here. And we're going to lose 2 electrons to get to neutral, right? I started out negative, I got neutral, so I was getting more positive, which means that I'm undergoing oxidation. Oxidation is loss of electrons, so this is happening at my anode. So that means then, functionally, in this beaker, what's happening is that I'll have sodium metal that is plating onto my cathode. So this cathode is getting larger, and it's getting larger with sodium metal on it. And at my anode, those Cl2 gas particles, right, because Cl2 is the elemental form, this is really high temperature. So when we form this, when we get rid of those electrons and form diatomic chlorine, then it's in its gas phase and it's going to leave the solution. So we'll have a bunch of chlorine gas coming off at the anode and plating sodium metal onto the anode. So that's kind of wacky. You can do this too, not just with molten salts like this, although this is sort of a cool and interesting application because we don't usually think about liquid salts. You can also do this in solution. If I have a high enough concentration of the ions in solution, they're going to do the same type of chemistry. And again, you have to run an electric current through. And an electric current, kind of from a chemist standpoint, is a flow of electrons. And the SI unit that we use is the ampere, or the amps. And we just abbreviate that with a capital A. And the relationship between current and maybe some of the other things that we've talked about in the past are the charge of all of the things. So in this case, the flow of the electrons is what's giving us our charge. So the charge on all of those electrons that are flowing around is equal to that current, which is in amps times time. So charge is measured in coulombs, and that's going to be equal to an amp second. If we're thinking about this in terms of the relationship between my units, or an amp is equal to a coulomb divided by seconds. So this is the relationship between a few of the quantities that we've talked about, and we can calculate this current given the right conditions and information about a redox system. So if I have copper sulfate, for example, in solution, so I have an aqueous solution of copper sulfate. It's not a molten salt in this case, it's dissolved in water. Then the copper is going to, if I run an electric current through it, it's going to pick up some of those electrons and it's going to be reduced, right? It's going to be reduced into copper metal. We call this electroplating. So we're plating out metal using the electrolysis process. So we're plating out this copper metal. So if we pass a constant current for 5 hours through the solution and plate out 404 milligrams of copper, what was that current that I had to use? Well, we can use this relationship, this balanced chemical process, to get us to that answer, because we have milligrams of copper, and we can go from milligrams of copper to grams of copper. And once I have grams of copper, then we're pretty well conditioned to go from grams to moles of copper. And because I know this balanced redox process, I can go from moles of copper to moles of electrons. And from the moles of electrons, I can get the charge. And I care about the charge because of the relationship that we just talked about. The charge is equal to the current times the time. So if I'm looking to find the current, then I can take the charge, divide it by the time that I ran it, which is given, and I will be able to find the number of amps. So let's set this thing up. If I want to go from milligrams to grams, then I just need to know that there's 1,000 milligrams in a gram. My copper. So that gives me, and we can kind of do this stepwise, this many grams of copper, and then I can go from grams of copper to moles of copper using the periodic table, because I'm a chemist. So 63.55 grams for every 1 mole of copper. And then I can go from moles of copper to moles of electrons using my chemical equation, right? So for every 1 mole of copper that I have, I'm going to pick up 2 moles of electrons. Oops, 2 moles. All right, now to get from moles of electrons to charge, then I can use Faraday's constant, because remember that Faraday's constant is the number of coulombs per mole of electrons. So if I have 1 mole of electrons in my denominator here, then I can have my 9.6485 times 10 to the 4th, or 96,485 coulombs for every 1 mole of electrons. And then that gives me 1.226. I'm going to keep too many sig figs for now. Coulombs. All right, so we said that the charge is equal to, and I just solved for the charge. Charge is equal to the current times the time. So if I'm solving for my current, my amperes, then that's going to be the number of coulombs per second. So I have number of coulombs, so that means I need to get my time in my SI unit of seconds, right? So it's in hours right now, so I need to do the conversion from hours to minutes, minutes to seconds. You could do this all in one step if you wanted to. I like being explicit about it. You can do the 3600 though if you're snappy with that. And then we end up with 1.80 times 10 to the 4th seconds. We'd expect that number to be big because we're going from a larger unit to a smaller unit. And now we take this many coulombs divided by this many seconds. It's going to give me the current, which is what it's solving for. And then we end up with 6.81 times 10 to the negative 2nd amps. So pretty small current to get. I mean, that's not a gigantic amount of copper, but you did get copper metal out of a solution that looked like it just had dissolved salt in it, or, which basically just looks like water unless you have a really cloudy solution. So you essentially pulled copper out of the water, which is just so cool. And you could do it with a current of 6.81 times 10 to the negative 2 amps.